Okay, so this paper that I'm going to review on large-scale forcing of West Antarctic surface melt is actually a spin-off of a field program back in 2015-2016. It was a Year of Polar Programs affiliated project. How do we advance the slides here? Is it this guy?
It's the green. You got to point it.
Green. Okay. So this field program was called AWARE, and it was the Antarctic deployment of the ARM mobile facility. This is among the best atmospheric science equipment you'll get anywhere. We were lucky enough to deploy this for a year in the Antarctic, and we even got to West Antarctica. And West Antarctica, as was discussed this morning, and as Irina mentioned, it's very important for climate change and sea level rise. It's also very, very difficult to get to. Currently, West Antarctica is the second largest cryosphere contributor to mass loss and sea level rise. It's about 60% that of Greenland in mass loss, so it's very important. It's also difficult to get to, but we were lucky enough to get there. I was chatting with Matt Shoup yesterday about the scope of Mosaic compared to other similar programs, and probably AWARE is about 1/5 the scope of Mosaic in its overall scope, and I had to do a huge amount of heavy lifting to make AWARE happen, so I imagine Matt had to do exponentially more to make Mosaic happen. But nevertheless, it was a very successful program, and 6 or 7 years downstream, I'm most jazzed by the papers that have kind of used AWARE as a stepping stone to go further, look at a bigger picture, larger areas, larger timescales. And this paper by SAO graduate student Ryan Scott is one of them. So I mentioned we were lucky enough to get to West Antarctica. We were actually extraordinarily lucky because we were able to sample one of the biggest melt events in the past 40 years satellite record. As you can see here on the left, this melt event impacted nearly all of the Ross Ice Shelf and all of the vulnerable ice sheets and ice shelves along the Amundsen Sea Embayment. And where we were located with our instrumentation for AWARE, there's a little WD there. So we were just outside the most intense melt zone. We were just in the region where the melting was kind of incipient, but that was actually an advantage because with our instrumentation, our radiometric instrumentation and remote sensors, we were able to diagnose all of the components of the surface energy balance that led to the onset of the melt event. And what we discovered is that when you have a melt energy flux, which is the net of surface energy balance, when this melt energy flux remains positive for more than one diurnal cycle, if you have that and you're near freezing, that will induce enough surface melt that's detectable by satellite, by passive microwave imagery. So very, very lucky in that respect. This melt event was driven by essentially an atmospheric river, a huge, there's an Amundsen Sea blocking high, a huge amount of moisture transport over a sea surface temperature anomaly, just slammed West Antarctica and the Ross Ice Shelf with moisture and heat and caused this melt event. And again, it happened after we were gone in 2017. So the question is this happening even more frequently as time goes on? Let's see, so did I skip one? No, so a little more motivation here. It turns out that there are at least 3 mechanisms for inducing surface melt related to clouds in the atmosphere. And this is more motivation for understanding the large-scale meteorology thoroughly. The first mechanism is simple thermal blanketing. When you have an atmospheric river or something bringing lots of low cloud cover over an ice sheet or ice shelf, you will basically cause a lot of warming, drive that melt energy flux way positive for a little while, and induce a lot of surface melt. But you don't just need those optically thick low clouds. Turns out thin clouds can do the same thing. This was discovered over the Greenland ice sheet by Bernards et al. Back in 2013. They published it. It was during the 2007 Greenland melt event that they discovered this. When you have these low liquid water clouds in the range of 10 to 40 grams per square meter in liquid water path, they cause a certain amount of long-wave heating, but they also transmit a certain amount of short-wave radiation to the surface, so that they have this all-wave radio effect, which can drive the melt energy flux up high enough and long enough to induce some surface melt. And finally, we have phone winds that can happen in lee of any high terrain, depending on the conditions. And that also happens in many places in West Antarctica. And Jerry Zoe has a nice paper in Quarterly Journal of the Royal Meteorological Society describing phone winds over West Antarctica. So these mechanisms can function independently or sequentially or in concert with each other, and so this is another reason to thoroughly understand the meteorology that might influence surface melt. And finally, a reason for concern is that West Antarctica, unlike Greenland, West Antarctica is a marine ice sheet. It's situated, it rests on topography that's below sea level and slopes downward as you go inland. And so what happens is as the warming ocean melts and erodes the grounding line and drives it further inland, the thickness of the ice sheet at the grounding line becomes thicker and thicker, and just by basic conservation of mass, that means that the ice sheet will accelerate in its outflow. So the system is mechanically unstable. And in particular, the Pine Island and Thwaites Glacier region, it's often referred to as the soft underbelly of West Antarctica because this topography is connected geographically with virtually all of West Antarctica. So that's a particularly intense region of concern. But then we also have the floating ice shelves which are extensions of the ice sheet out over the water. These are anchored to various pieces of terrain, and so they provide essential buttressing, which tends to retard the flow of the ice sheet. And what happens when you have surface warming and you have melt ponding and pooling of water, that water can percolate down through the ice shelf, weakening its structure by a process called hydrofracturing, cause a breakup of the ice shelf. This happened in the Larsen B ice shelf back in the early 2000s. That was the most dramatic example. But this is, we need to realize that this can happen anywhere as surface melt events become more frequent. So, to make sense of all this, try to make a contribution, we obviously have to look for teleconnections. And so that's what I'm going to be reviewing. The paper is Ryan Scott et al. We published this in the Journal of Climate in 2019. And so we're obviously going to be looking at El Nio Southern Oscillation. And so events are expected to increase in a warming climate. And we're also going to be looking at the Southern Annular Mode, which is the leading mode of Southern Hemisphere extratropical variability. And then the second and third leading modes are known as the first and second Pacific South American patterns. In particular, the PSA1 pattern exhibits that classic Rossby wave train structure with a center of action off the coast of West Antarctica, and it's often interpreted as the Southern Hemisphere extratropical response to ENSO. Okay, so these are our methods that are pretty thorough, that Ryan did a very thorough job with this. Just some of the procedures he went through here. For surface melt detection, we're using satellite passive microwave data, 18 gigahertz or K-band horizontally polarized brightness temperatures using a 30K anomaly threshold method that was developed by Jay Zwally at NASA Goddard and then well tested by Marco Tedesco. Atmospheric reanalysis, this was before ERA 5, just before, so he used ERA interim, and he's computing anomalies in the 700 millibar geopotential height, 2-meter air temperature, and 10 meter wind fields, and computing daily means for the 6-hour fields. Clouds and radiation. The cloud properties are going to come from the AVHR Polar Pathfinder and the NOAA Climate Data Record, which is a NOAA climate data record. And then for radiative transfer, we use the streamer radiative transfer model, which is well tested at high latitudes. And then from that, we develop our West Antarctic melt season synoptic climatology, performing EOF analysis of the 700 hectopascal geopotential height anomalies to determine our own derivation of the SAM, PSA1, and PSA2 modes, and checking that against the standard indices. And then we use the k-means clustering analysis to isolate these isolate a total, what turns out to be 9 dominant patterns of atmospheric circulation, and then we calculate surface melt anomalies from the satellite passive microwave corresponding to each of these patterns. And then we attempt to derive relationships between tropical sea surface temperature and other things, as I'll show in the following set of examples. So this figure shows regression maps of the PSA signatures and the SAM signatures in the extratropical southern hemisphere, 700 millibar geopotential heights and 2-meter temperature fields. And these are regressions of daily anomalies onto the index of each mode. And we notice here that the intensification of the SAM leads to widespread cooling in West Antarctica, while the PSA patterns favor the advective warming of the entire Ross Sea sector. And then here we have some correlations of each mode with the global sea surface temperature anomalies. And these implies significant relationships with sea surface temperature throughout the Pacific Basin. And in particular, just kind of summarizing these somewhat complex figures, we have sea surface temperature structures that are characterized, that when they're characteristic of La Nina events, they favor a positive SAM, a negative PSA1, positive PSA2, and these ultimately lead to stronger circumpolar westerlies in a deep Amundsen Sea low, and this generally inhibits melting in West Antarctica. But then when you have sea surface temperature structures characteristic of El Nino events, this favors a negative SAM, a positive PSA1, and a negative PSA2, and this leads to weaker circumpolar westerlies and frequent blocking over the South Pacific. And the PSA1 correlations are significant across a broad area of central eastern tropical Pacific, and this is consistent with amplification of the PSA1 via ENSO Rossby wave forcing. So here we just have the historical impact over our 4-decade test period of the impact of the SAM and the ENSO on surface melt conditions in West Antarctica as regressions of the seasonal melt anomalies against the SAM, PSA1, and then on the far right, the inverted Southern Oscillation Index. And the intensification of the SAM leads to cooling and reductions in melting on the Getz and Sulzberger and Ross ice shelves. The Getz ice shelf is right there, Sulzberger is here, and then of course the eastern Ross ice shelf there. But then when we have positive El Nino episodes, these favor enhanced surface melting areas critical to the stability of the West Antarctic ice sheet, all the way from Pine Island and Thwaites Glacier, all the way through to the Ross ice shelf. So here's the main result here is our climatology, our 9 synoptic patterns that came out of the K-means clustering. I don't have time to review every single one of them, but I'll mention 3. I'll start with pattern 7. This one is the sledgehammer. This is responsible for all the big melt events and the big atmospheric rivers that have slammed West Antarctica over the past 40 years. And this is characterized by a negative SAM and positive PSA forcing, and it creates a blocked low-pressure system which drives strong meridional invection of heat and moisture into West Antarctica. It also can cause foehn winds in the lee of the Edward VII Peninsula around here, putting that terrain under stress. And these positive anomalies of 2-meter temperature and cloud cover cause the widespread enhancement of downwelling long wave radiation through that thermal blanketing mechanism. And in contrast to that, we have pattern 2 up here at the top, and this is the strongest positive SAM signal, and it's often present during La Nina events, and this drives a deep low over the Bellingshausen Sea, as you can see here, and that induces outflow of continental polar air, so it's basically pulling air away from West Antarctica out to sea, and that, of course, inhibits melt. And finally, I'll just mention pattern 5, which is in the middle, and this kind of looks like pattern 7 flipped somewhat. This is characterized by a weak negative SAM and a strong negative PSA2, and this actually causes a northerly influx of marine air down along the Antarctic Peninsula, and this can induce cloud anomalies and downwelling long-wave radiation on the Filchner ice shelf, and also foehn winds on the George VI ice shelf. So the base of the Antarctic Peninsula is impacted by this pattern in terms of surface melt. And then finally, with all this analysis, we decided to define an Amundsen Sea blocking index, analogous to the Greenland blocking index. And here our Amundsen Sea blocking index is defined as the area-weighted mean 700 millibar potential height anomaly over the Amundsen Sea from 55 to 70 south and 230 to 260 east. Significantly correlates with patterns 7 and 9, which are strong melting patterns. And then just looking at the trend over our 4-decade period, there's a negative trend in our ASBI, but it's not statistically significant. Then it's followed by a statistically significant trend beginning around the turn of this century. And just another more two-dimensional way to look at this, these are just trends in the large-scale forcing for these 2 periods prior to and after Y2K. During period 1, the Southern Annular Mode intensified, but it's not showing statistical significance except over East Antarctica. And then there's a statistically significant increase in the G-potential height for period 2, especially in the Amundsen and Bellingshausen Seas. So our conclusions here. Of our 9 700 millibar geopotential height patterns, 6 of them favor melting somewhere in West Antarctica, and 3 of them tend to inhibit melt. And our analysis identifies linear trends in West Antarctic ice sheet and ice shelf surface melt with an inflection point somewhere around, roughly at the start of this century, as we see here. And our Amundsen Sea Blocking Index helps to explain surface melt in various sectors of West Antarctica. For example, the Ross Ice Shelf, the Getz and Sulzberger ice shelves, Abbott ice shelf is back up here. So it's not just a general regional index, it helps explain melting conditions at various segments of the Amundsen Sea Embayment. So I think I'm very happy with this work, very thorough piece of work done by our graduate student, Ryan Scott, who is now at NASA Langley. I'll stop here and take any questions. Question there.
Yeah, thank you. That's really curious. The event that I described had the opposite pattern, actually. So it was positive SAM, it was La Nina, and it was this extraordinary heat wave over the Antarctic Peninsula, also touching on the base of the peninsula, so it was the Ellsworth land, but not spreading over the WAIS. So I wonder if the events you're talking about, which are in the totally different pattern, right? Like it's actually, that's what you said, it should be inhibited melt in the WAIS. But so either we have the dipole, right? That was already described in the literature, or it's that such events can still happen during the patterns which actually should inhibit melt over the WAIS.
Well, generally speaking, I think your event is consistent with the ones I'm describing, and that the peninsula will behave differently than the WAIS. They'll kind of be in opposite phases. And of course, we think of the peninsula warming steadily all the way until roughly 1999 or so, and then cooling. That's what David Turner showed, as the SAM changes its behavior. But that's just a general trend. That doesn't mean there couldn't be individual events that kind of buck the trend. So yeah, I think the positive SAM is going to favor that warming on the peninsula, whereas it inhibits it over West Antarctica.
So I think that's really, that's this dipole that we have, either WAIS or a peninsula that is actually more affected by melt due to these teleconnection patterns.
So what exactly were the dates of your event? I could probably look up what our indices are in our climatology and see if we could explain it in terms of one of those patterns. I'm sure we could.
Yeah. Maybe we can compare also, and that's
okay.
Well, I would just say I was curious about this mismatch, but thank you.
Sure.